everyone, thank you so much for joining the video. Today we're going to be looking at periodic trend in structure and melting point. So we're going to be looking at the explanation of metallic bonding as strong electrostatic attraction between cations and delocalized electrons, and explaining giant metallic lattice structures. We're also going to explain solid giant covalent lattices of carbon and silicon as networks of atoms bonded by strong covalent bonds. And then we're going to go on to explain physical properties of giant metallic and giant covalent lattices, including melting and boiling points, solubility, and electrical conductivity in terms of structure and bonding. Lastly, we're going to explain the variation in melting points across periods 2 and 3 in terms of structure and bonding. Now we're going to talk a bit about metallically bonded compounds and also giant covalent structures. So metallically bonded compounds form giant metallic lattices, and they have very strong electrostatic forces of attraction between the positive metal ions and the delocalized electrons in the C. So what the structure kind of looks like is you have the positive ions, so these are all the cations, the positive ions, and then you have the electron C, which is around all the cations. For giant covalent structures of carbon or silicon are networks of atoms bonded by really strong covalent bonds, and therefore giant metallic and giant covalent lattices both have very, very high melting and boiling points, because it takes a lot of energy to overcome the strong electrostatic attraction in the giant metallic lattices, and also the very strong covalent bonds in the giant covalent lattices. And so both of these structures are also insoluble because of this same reason, because a lot of energy is taken to overcome all the bonds. Giant covalent structures can't conduct electricity as there are no delocalized electrons or ions, whereas giant metallic structures can conduct electricity as they have a sea of delocalized electrons, so free electrons, which carry the electric current. Now we're going to look at the trends in melting and boiling points of the period 3 elements. So this is a graph showing the boiling points and the melting points, and we're just going to quickly discuss through. So sodium, magnesium, and aluminium all have giant metallic structures, and so there are lots of strong electrostatic forces between the positive metal ions and the negative electron cloud, and these kinds of forces take a lot of energy to overcome, and so this leads to a generally very high melting and boiling point compared to the nonmetals. Now, the melting and boiling points increase from sodium to aluminium because of the increase in ion charge. So if we think about sodium, it forms Na plus ions. But if we think about magnesium, it forms Mg2 plus ions. And because Mg2 plus has a bigger ion charge, the metallic bonding is stronger than in sodium. So if we had sodium chloride and magnesium chloride, for example, the metallic bonding in magnesium chloride would be bigger than in sodium chloride. And so because the metallic bonding gets stronger, that means it takes more energy to overcome. And so the melting and boiling points of magnesium will be higher than for sodium. Silicon is a giant covalent structure, so it has lots of strong covalent bonds throughout the structure, which take a lot of energy to break. And so this leads to a high melting and boiling point. Phosphorus, sulfur, and chlorine all have simple molecular structures, so there are very weak van der Waals forces between the molecules that don't take very much energy to overcome, and this leads to generally very low melting and boiling points compared to for the giant metallic structures and for the giant covalent structure of silicon. And so for these simple molecular structures, their melting and boiling points actually depend on the size of their van der Waals forces, and this depends on the number of electrons, like we've learned before, and how the molecules can pack together. And if you remember back to how these elements exist, so we have sulfur, which goes round in 8s, and then we have phosphorus, which goes round in 4s, and chlorine, which is diatomic, so goes round in 2s. And so the van der Waals forces in S8 is bigger than in P4, and the van der Waals forces in P4 are bigger than in Cl2, just because S8 has way more electrons and it's a lot bigger, and so the van der Waals forces will be well, there'll be a lot more of them, and so more energy is taken to overcome the van der Waals forces in the S8. And so sulfur, the melting and boiling point of sulfur will be higher than for phosphorus and chlorine. Now we're going to have a look at the trend in melting and boiling points of period 2 elements. So as you can see, it peaks towards group 4, and this is because lithium and beryllium both have metallic bonding, and so they have very high melting and boiling points. Beryllium has a higher melting and boiling point compared to lithium because it forms 2+ ions, so it has a higher charge density. So these 2+ ions are more attracted to the negative electrons in the delocalized C, and so the strength of metallic bond in the beryllium is higher than in lithium, and so more energy is needed to overcome these strong metallic bonds, and so the melting and boiling points of beryllium are higher than for lithium. Boron and carbon are both giant covalent structures, so they have lots of strong covalent bonds which take a lot of energy to overcome, and their melting and boiling points are actually higher than those for lithium and beryllium. And then nitrogen, oxygen, fluorine, and neon are all simple molecules, so they only have very weak van der Waals forces between the molecules, which don't take a lot of energy to overcome. And all of their melting points and boiling points are very, very low, and they're all actually quite close to each other. And that's because nitrogen, oxygen, and fluorine all come as diatomic molecules, so all of their sizes are very similar. So now we're going to look at some questions. The first question says, state the type of structure shown by a crystal of silicon and explain why the melting point of silicon is very high. And so silicon has a giant covalent structure. And it's really important to remember that it's a giant structure, because you might think that because it's a non-metal, it forms a simple molecular molecule, but it actually has a giant covalent structure. So it still has the covalent bonds, but it forms a giant structure. And so it has a really, really high melting point because these strong covalent bonds take a lot of energy to overcome. So giant covalent, and there are lots of strong covalent bonds which take lots of energy to overcome. And that's why we have a very large melting point. And then for B, state the type of structure shown by crystals of sulfur and phosphorus and explain why the melting point of sulfur is higher than the melting point of phosphorus. So sulfur and phosphorus are both non-metals, but they don't form giant structures. So they are simple molecular structures. And so that means that they have very, very low melting points compared to the giant covalent structure of silicon. And so the melting point of sulfur is higher than the melting point of phosphorus, because when we draw out the molecules, the sulfur molecule is much bigger, because sulfur exists in 8s and phosphorus exists in 4s. And so the molecule of sulfur is much, much bigger. And this means that it has stronger van der Waals forces between the molecules, and so they take more energy to overcome. So we have that sulfur exists as 8 atoms in a molecule, whereas phosphorus is 4, and so that means that sulfur is a bigger molecule, and so has more electrons and therefore stronger van der Waals forces, because they both have van der Waals forces as they're both simple molecular structures, but it's just because the sulfur is much bigger, so it has stronger van der Waals forces between the molecules. And so more energy is needed and so that's why we have a larger melting point for the sulfur compared to the phosphorus.